Talks all relating to time integration methods. And first is Colin Clancy from Environment Canada, who's going to talk about semi-implicit predictor-corrector methods for atmospheric flows.
Okay, thank you very much. So good morning everyone. So for the next while I'm going to be entertaining you with some details on time integration schemes. So this is work that I've been carrying out with Janusz Pudikiewicz at RPN in Environment Canada. So the backdrop to all this work is a new atmospheric model which is being developed at Environment Canada. Janusz has been working on it for the past number of years. It's described in two papers of his in 2006 and 2011. So it's a finite volume model on an icosahedral grid. So in the 2006 paper, he goes through the grid, the operators, and looks at reaction and diffusion equations on the sphere. And then the 2011 is a full shallow water model with this discretization. Okay, so then I came along and had to do something and ideally not ruin that nice model. So we decided we'd look at some time schemes and see if we can improve it a bit. So in all that work, he was using the fourth order explicit Runge-Kutta, which is great, but moving forward to more complicated models, obviously something more stable might be needed, more efficient. Okay, so I wanted to maybe try something different than the traditional semi-implicit leapfrog approach. Okay, so this has been, of course, a classic scheme of André Robert from the 70s, I suppose, and has been used ever since. But as everyone knows, there are a few problems with it, mainly being the computational mode, for which one needs to apply the Robert-Asselin filter. And this, of course, damages the accuracy. Despite this, it's still been used for the last number of decades, and it is a great scheme. In one of the papers of Williams, actually, he gives a list of many of the models and centers that are using this scheme. So it has stood the test of time, but you know, time moves on, and there's no harm looking for some improvements. So recently, there have been a few attempts to go further with it. So I mentioned Williams in 2011 in an earlier paper. He introduced a modification to the Robert-Asselin filter. So this would allow you to keep the semi-implicit leapfrog, but hopefully improve the accuracy, keep your second order. There's a recent paper by Dern and Blossi, just out. So they looked at a number of different schemes of semi-implicit type, a whole family of them, and we're comparing. So in a sense, my talk is a similar kind of idea. Carr, I'll mention too. He described the predictor-corrector method, which I'll come to in a while. So I'm going to keep everything nice and simple, equation-wise for now. So we just consider some general ODE system where we've been able to separate the linear terms and the nonlinear parts. So we'll assume that we can do this without any controversy for now. Okay? So of course, the traditional semi-implicit is a leapfrog-based method centered on the nonlinears and a trapezoidal implicit method on the linear terms. Okay, so that's great, but of course normally, as I said, we need our filter on it. So the approach we chose to take is a semi-implicit predictor-corrector approach. So basically, first of all, it's a two-stage approach where first we look for an intermediate stage, which we call psi star. So anything with a star is your predicted intermediate level. Okay, and then, of course, we look for a corrected new time level, n+1. So to begin with, keeping everything nice and general, so we're allowing potentially a time derivative over 3 levels, some implicit scheme on the linears over 3 levels, and then some, 2 levels on the new one, and then some nonlinear, or something on the nonlinears. So basically, any of these coefficients, lambdas, are all for the linear terms, the nus for the nonlinear terms, and as I said, anything with a star is a predicted level. Okay, so obviously there were many choices, and I could spend all day going through all the different options, but I won't, don't worry. So we focus particularly on two linear approaches. Okay, so let me just stress again and be pedantic about it. So again, our linears, remember, we're going to take an implicit scheme. The nonlinears, it's going to be a predictor-corrector approach. Okay, so the two, after looking at various different options, the two implicit schemes I'm going to go for, one is the trapezoidal, well known, okay? The other is, I'm using the notation from the Dern and Blossi paper, They reference back a paper by Thornburg and Driscoll a bit back, which also used this scheme. It's a modified Adams-Moulton, I believe. I think that's where the star comes from. So, so this is it. So again, another implicit scheme. For the nonlinear terms, the explicit part, we focus on three predictor-corrector methods. So the first is leapfrog trapezoidal, which, as its name suggests, you have a leapfrog method on the predicted stage, trapezoidal on the corrector stage. This Kurohara back in, I believe, the 60s talked about this. Second was discussed in that paper by Carr, which I mentioned earlier. So it's an Adams-Bashford trapezoidal, ABT we'll call it. So it's a second-order Adams-Bashford on the predictor, and then a trapezoidal on the corrector. And then the third one I threw in was a third-order Adams-Bashford-Moulton scheme. Okay, so again, it's a Adams-Bashford second-order on the predicted stage, and this corrector, and the whole thing is third-order. Okay, so taking these, obviously there are lots and lots of combinations we can do of the two, for the implicit schemes and the explicit schemes. So I'll give two examples. These are ones I'll look at and explain my notation. Okay, so hopefully it seems logical. So here we'll have the first will denote your implicit scheme. Second, the explicit part. So this is a trapezoidal Adams-Bashford trapezoidal. So basically trapezoidal on your linear parts at both predictor and corrector stage, and then the Adams-Bashford trapezoidal predictor-corrector scheme. Another possibility, the AM2 star scheme coupled with the Adams-Bashford-Moulton scheme gives us AM2 star ABM. Okay? So hope I haven't lost anyone so far. That's logical, hopefully. Okay, laughs rather than screams. That's grand. Okay, so obviously, yeah, lots of different combinations. So how to distinguish what's good or not. So we went down the road of nice linear stability analysis. So the classic approach of let's just take simple ODE with one fast frequency, one slow frequency. Let's treat the fast one as our linear and treat that implicitly, or slow one as a nonlinear, treat that explicitly. And we look for regions where our amplification factor is less than 1 or less than or equal to 1, which is what we want for linear stability. Okay, so the reference semi-implicit, this is our SILF, semi-implicit leapfrog. That's what I'm calling the classic Robert scheme. Okay, this is plotting in a non-dimensional plane of the slow frequency by the time step, and on the vertical axis, the fast frequency by the time step. So this is the kind of stability regime you get. Okay, so anything in white is stable, anything in a gray is unstable. Okay, so the tradition looks great, but that's not the whole story, of course, because in reality we would have to add the filter, the Robert-Asselin filter, which would lead to damping and damage this nice picture. Okay, but ultimately this is the kind of thing we want to at least do as good as, or possibly do better at. Okay, so it turned out there were we ended up with 4 combinations which gave nice stability regimes. So this is top left, the TABT, so trapezoidal, and then on the implicit, and Adams-Bashford trapezoidal. The AM2 star with the ABT, the AM2 star with the leapfrog trapezoidal, and actually, so the AM2 with all the predictor correctors I showed. So remember, just going back to compare, so we want something, so that was at the non-dimensional parameter 1, so we want something roughly that shape in stability regime, and, wrong way. So all of them are as good or a little better in some cases. I also, of course, have the contours of which show a bit of damping, but that's okay because remember the filter will damp your semi-implicit leapfrog anyway. Okay, so this one, I thought at first didn't look great, had a bit of concerns for it, but actually in reality, in practice, it turned out to be nice enough. So we'll stick with these 4 for now. Okay, so that's great. Linear ODE, but of course we want to do a little bit more if we want to predict the weather ultimately. So back to the shallow water model, which I mentioned, described in Predictor-corrector in 2011. So we implemented all these schemes in this shallow water model to compare with the reference. Of course, with an implicit scheme, as we all know, we'll end up with a Helmholtz equation to solve, and for this we use the iterative generalized conjugate residual scheme, the k equals 4 version, which is described in Smolarkiewicz and Margolin in 2000, and it's used in a number of other papers. In all these runs, we use no explicit diffusion. The filter of Williams is used for the reference semi-implicit leapfrog. Okay, so actually, yeah, I should have mentioned before. So all of the predictor correctors, of course, go over a number of time levels. They do have computational modes, but all of these are highly damped. So the nice thing about them is you don't need to add a filter, whereas for just the leapfrog you do. So all our simulations carried out on an icosahedral grid with a resolution of about 112 kilometers. That's about 40,000 nodes. For the reference, we're just comparing time steps here. So we just went with the one grid higher, the next division, which is about a 56 kilometer resolution. Sorry, so this is a reference for computing errors. Just said that. So this is confusing myself now, so probably confusing you. So all the runs, yes, are at the grid 6, the 112 kilometers, and we'll test them with all the time schemes and test them against the reference semi-implicit and against the explicit Runge-Kutta, because that's what's been used so far. So then, of course, for some of the schemes, we want a reference solution to compute errors where no analytic solution exists. So for this, our reference is a higher spatial resolution icosahedral with the Runge-Kutta explicit at a 90-second time step. And so we come to our old friends, the Williamson et al. Test cases. So the first one I'm going to show is number 5, the flow over the mountain, and I'm going to be plotting the normalized L2 error norm. Okay, so first of all, we're taking a time step of 240 seconds. This is fairly low. This dashed line down here is the Runge-Kutta, explicit Runge-Kutta. So of course, we'd probably expect that to be a bit better, being 4th order. But this trapezoidal Adams-Bashford trapezoidal actually does quite nicely and matches it. All the rest are comparable. Okay. The big thing is, okay, well, we'd expect the Runge-Kutta to be a bit more accurate, but it's stability we're interested in here. So we up the time step a bit to 600 seconds. Okay, so the Runge-Kutta explicit is still the best, fine, but the others still are still all comparable, and the trapezoidal Adams-Bashford is still a little bit better than the rest. The nice thing is we can go further to 900 seconds. The explicit Runge-Kutta won't go this high, so I'm just still plotting the 600 one here just for comparison. So our errors have increased a little bit. So let's see the scale on this. Actually, not that much. So it's the same horizontal scale. So the errors haven't increased greatly, and we can go at a much larger time step. So that's quite nice, and they're all comparable. The black is the semi-implicit reference of Robert. So it compares nicely with all of them. Next, we move on to the Rossby-Horowitz wave. Same errors again. So first of all, the short time step, 240 seconds. Actually, in this case, they compare quite nicely with the explicit Runge-Kutta. But this being a more challenging case, the explicit scheme won't go any higher with time step. So in all the plots to follow, this Runge-Kutta is still the low 240 seconds. We couldn't get any higher than this. The other schemes are fine, though. We can keep taking higher and higher time steps. And at 600 seconds, the errors haven't increased greatly. Strange blip aside. But it's still, they're all holding their stability and accuracy quite nicely. At 900 seconds, of course, now the semi-implicit leapfrog, the Robert method, no longer will run stably at this scheme or at this level, but all the predictor correctors will. So this is nice. We can push it quite far in terms of time step and still hold the accuracy. They're a bit wibbly but the vertical scale is still the same, 1.6 by 10 to the power 3. So our accuracy hasn't actually degraded significantly, and we're able to go to much higher time step. So this is all nice. So okay, so there's of course should be a catch. So now we look at efficiency. So because we're using a predictor corrector 2-stage, we have 2 elliptic solvers to solve 2 elliptic equations, 2 Helmholtz equations to solve each time step, as opposed to just one for the semi-implicit. So it's as I said, we're using an iterative scheme. So I'm going to plot this is for the mountain case at the 600 second step. So we plot the total number of iterations at each time step to give us some kind of measure of efficiency or cost. Okay, let's go through this. So the nice thing is, anyway, so here is the semi-implicit leapfrog in green. So roughly we're talking about 5 or 6 iterations are needed to get to a specific what's the word I'm looking for? Accuracy, yeah, convergent, that thing, yes. Tolerance, thanks, John. So to get to our specified tolerance, we needed 4 or 5 calls. But the nice thing is the total, if we look at the trapezoidal Adams-Bashford trapezoidal, it's roughly the same, and actually some of the others are comparable or slightly better, and that's their total number. So that's the number of predictor steps plus the number of corrector steps. So it doesn't actually, it's not like you're doubling your cost because you're taking 2 solves, calling the solver twice. It's basically because you're predicting, you're getting closer to the solution, so your second call doesn't need to do as much work to get to your answer. Okay. So to summarize all this, so we've introduced these semi-implicit predictor-corrector schemes. Okay, so kept the framework general to start, so there's many other possibilities. You could spend lots more time doing different combinations. Who knows, maybe even taking a different implicit scheme at each step could work, I don't know, didn't try that. They're stable, which is nice. The very nice thing is no time filter is needed. And also the efficiency doesn't seem to be greatly affected yet, not in the shallow water case anyway. Okay, so future work. So future tests with the 3 dimensions. This is something I guess I say at the end of every talk, but I think this time it's actually going to happen because the model is actually almost ready as it's a 3-dimensional version. So it's something we'll definitely be looking to implement because we won't want to go with the explicit scheme in the 3-dimensional version. In addition, we're looking to continue with time integration work and compare it with some other approaches, maybe semi-Lagrangian, maybe exponential integrators were mentioned yesterday. So just to compare them all, see which works best for this model. Okay, so that's pretty much me. So lots more information in a paper about to appear in JCP. These are all my references that I mentioned. So thanks very much.
Now, I'm wondering, since you're reviewing all this area, why you're sticking with 3 time level schemes? Because on a 2 time level scheme is simpler, and you have all these options. And I thought you could probably do just as well with a 2 time level scheme.
Yeah, no particular reason. It's just.
Okay, so
yeah.
In principle, yes, but you just haven't.
Yeah, it was. Yeah, haven't really nailed my colours to any mast yet. It's just kind of
It just
keeping
seems
general.
3 time level seems an unnecessary complication once you start looking in this direction.
Yeah, true. I guess maybe that'll, yeah.
On your stability plots, you had one of the schemes had a region of instability, and then you said it runs fine, but it runs fine.
Yeah.
Is there any way you can kind of put your model in that regime?
I guess, yeah, it would be worth if you wanted to really, yeah.
Have you any idea why the stability analysis doesn't?
Well, I mean.
Doesn't.
Well, I guess it's more a fact that we've just been lucky probably so far and haven't hit that regime, to be honest. That's, I'd say, pretty much it. That would be my guess. So even that graph would suggest, okay, so far in these nice shallow waters we haven't hit that regime, but in theory you could, so probably best avoid that one and go with the others, which are, less likely to blow up. But yeah, one might be curious actually to just force yourself into that regime and be worse. Why not?
I've tried, actually.
Okay. Does it work? Or
no, I can't. I've done similar tests with it. We found that region. I can't make it. I can't see that it's a problem.
Okay. Fair enough.
One last question, Mika.
You showed this nice stability analysis looking at the imaginary parts. But does it mean that you are restricted to pure standard differences, spatial operators, or because if you have, for example, up-in bias schemes, higher order up-in bias schemes, it becomes also, for example, negative real parts in your probability analysis.
Yeah, I guess that would probably better to generalize the. But then it gets so complicated because you have real parts and imaginary parts, and it's just harder to plot. Yeah, but you're right. It's definitely worth doing more. But in this model, anyway, I haven't had any issues yet with it. But it would be more rigorous to consider every real parts imaginary. So.
Excellent. Thank you.